Yeah, no, it's 2. It's me twice. Current viewers 2. If I hit this button, does it go to 0? I think it's just me twice. By the way, hello and welcome. Goes down to 1. Okay. Someone's watching me. How's it going? Welcome. Hello, hello. Hope everybody's doing well. Welcome, welcome. So the idea here is, I was working on this problem the other day. It's a very interesting problem, really involved. We're so close to finishing these problems. We got about 20 left. We've only got about 4 hard ones left, this being one of the 4 ones. And these hard problems they take so much time. Holy smokes. Can't handle how much time it takes to solve these problems. Which is okay. It's fine. It's just a lot. It's a lot of time. Excuse me. So, I think yesterday I tried to explain the problem. I have the previous video. You could see the Karnaugh maps. I tried to explain what they are. I'll try to explain the solution that I'm going to go for. So the solution that I'm going to go for, I believe, is exponential. It's definitely exponential, but it might even be like 2 raised to the n squared, 2 raised to the n quantity squared in terms of big O time complexity. I'm not sure exactly. Yeah, I'm actually not even sure. Let me think about it. It might be. I've been thinking about it for a while. So basically, what I'm looking at is this was incorrect, actually. This ended up being wrong. What we end up using is 2 raised to the n minus k times 2 raised to the k, which is just 2 raised to the n. And this is for each 2 raised to the n, we have this 2 raised to the n sort of set of things to consider. And this term comes from all of the different ways to group, like for a group of 16. No, it's not quite right, is it? Yeah. A group of 16. No. I don't know. I'm stuck on something. I'm not sure. Super conflicted. Like, I just don't totally understand. I think once I write the algorithm, then I can evaluate what the runtime complexity is, because I'll explain what I end up doing. It's not totally formulated yet, but it is. Let me think here. Excuse me. $16 is 2 raised to the n though. 2 raised to the n, right? Checking all 16, right? That is 2 raised to the n, and then checking for groups of 4. A group of 4 is 2 squared. There should be 8 of them. Although there's more than that for groups of 4. 2 squared by 2. 2 squared by 2 squared. No, there's way more than 4, right? You have 1, 2, 3, 4, 2, 3, 4, and then you've got like that in a few ways. Same thing here. Same thing there. Same thing here. Even here. Like, there's a lot of different ways you can get 4 ways. Maybe what did I miss? I'm doing something wrong. Maybe this was the correct thing. I think this was correct. I think maybe the approach that I'm going to take though is I don't know now. Huh. No. Huh. A group of 4. There is only 4 ways you could select. Yeah, these should all be this only should be 4 of these. There's only 4 ways you could do 4 choose 2, right? That gives you 6. Yeah, but that's not true. I'm so confused now. Basically, when you have 4, a selection of 4, you have a selection of 4, it means that 2 of these are constant throughout the whole, right? It says A, B. 4 is choose 2, there's only 6 different ways you could select these. And I guess there's 4. I'm actually really confused now. I don't know if the algorithm I was thinking about writing works. I was going to write something that's sort of a brute force approach to this problem. I don't know now. Oh, yeah. Okay, no. There is more than 6. Yeah, there is a reason why this is wrong. Okay, I got it. There's a reason why this is wrong. So the reason why it's wrong is because you're not doing 4 choose 2. You're actually selecting. There should be 8 of these. It's literally each of these possibilities, because the order matters, and it's going to be 2 booleans, or 2 boolean variables are eliminated, but which 2 you eliminate? And it's not just that you eliminate them, right? Because I think it's even more. I think it's actually the other way around. I think I did this wrong. I think it's 4 choose 2 times 2, which is confusing as heck, which is 12. And the reason is, rather than, there's more than 8, just 8, right? Because this is 8, this is 4, another 4, but then there's another 4 here. 1, 2, 3, 4. And there's even 4, 8, 12. There's even more than that. There's even like these directions. I think these directions, no, those count as the same one. But these, how about these ones? We're at 16. No, maybe it is. I'm so confused. I'm just utterly confused. How many different ways can you... A, B, AC, AD. And then you can say, oh, I know what the problem is. Right. It's actually, okay, I think I got it. All right. It's, you can have, it's confusing, but I think I know what it is. I think it is 24. And the reason is you could pick whatever this value is, 0, 0, right? Whatever, you're picking two different variables. You can have one of, let's say there's k of them, 2 raised to the k different possibilities, right? So because you could, whatever you pick k of these variables, it's actually even worse than I thought. This is n choose k times 2 raised to the k. And the reason for that, yeah, wow, okay, that's pretty wild. So the reason for that is there's, right, you have A, B, you know, A, it's no, it's not even that though. No, that's wrong. Even that's wrong. It's because you have A, not A, B, not B, C, not C, D, not D, right? 1, 2, 3, 4, 5, 6, 7, 8, and you're picking 8, choose 2. But these are exclusive, right? So it's not just 8, choose 2, right? 8, choose 2 would be too many. 8, choose 2 would be 56 over 2, which is 26, 28. It's not 28. It's pick. So really, it's one of these 4. So it's 4 choose 2 times 2 squared. So it is 24, right? So I was right the first time. Okay, so yeah, because yeah. So you end up with this n choose 2. So that's actually what I'm missing. Oh no, that's what I had here. Wait, I got it right the first time. Wait a minute. What? What? That's extremely confusing. I mean, I guess it does make a lot of sense, where it's 2 variables, and then you can pick 0 or 1 for each of those 2 variables. It could be varied any which way. Yeah. So, oh, okay. I was trying to figure the math out before. I mean, this is clearly at least quadratic. Or not quadratic, exponential. But my quote-unquote brute force algorithm to solve this problem, I don't think is going to work correctly then. What I was trying to do is say, all right, like, you know, just generate all of these binary sequences, right? And then really what I should do is I should actually loop through these, you know, sort of n choose 2, n choose k possibilities, where you select some values that aren't going to change. And you know what it is though also, well, does it really matter? I don't know, I'm conflicted here. Because then you can create the set by just walking through all of the other values once you selected that set. right, for each of these. Sort of what's left over, I guess. What I was thinking about doing, instead of writing any code that handles permutations, I was just going to generate all of the sort of binary compositions, like, you know, so if there's 16, you'd have all of these that you see all the way down, and then what I was going to do is say, okay, you know, to process each one of these, wherever you see a 1, you assume that that is a variable that's not going to change. And then obviously, for each of those not changing variables, you have k of them. You have 2 raised to the k different ways to either place a positive truth value or a negative truth value, right? The truth of the complement, right? For each of those ones, I guess. So for each of these cases, you process all of these individually. So here you have 2, here you have 2, you have 2, 2, etc., right? And then for each of those sort of subcases that you generate, you also generate the corresponding grouping, right? So like for the 1 that has 2, you would end up then generating I guess there'd be 8 of them. Yeah, like when A is always 0, right? There'd be 8 of these. So it'd be the other 2 raised to the n minus k values. That's kind of where I was getting 2 raised to the k times 2 raised to the n minus k. That would generate that set. That gives you 2 to the n time for each of these, and then there's 2 raised to the n of these. So that ends up giving you 2 raised to the n quantity squared, which I think is what you get with this sum. I think this summation is bounded by 2 raised to the n quantity squared, which seems a bit odd. I don't really have a proof for that, but I think it's true. May be able to prove it if you apply induction. Maybe you'll prove this using induction. But the thing that's really kind of got me thinking. Excuse me. Hoo-wee. 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 The thing that's got my attention, the thing that's got me is yeah, each of these cases, each of these 2 cases will have these 2 raised to the 3rd different sets. So then here you have 4 by 4. Yeah, every one of these ends up giving you... And this just outright gives you all of them to the 16th, and this gives you none of them. That case is... Well, there's 2 to the 16th different possibilities, though, and all of them give you just 1. What does that mean? What do each of these mean? All changing or none of them changing? If none of the variables change, in both cases you got 16 things to consider. Ah, okay, I see, I understand. The reason why this looks so different from the other one is because here you do the 4 choose 2. There's a bunch of different ways to do that. Right, it would look like, you know, 1, 2, 3, 4, 5, 6. All right. That's because you're breaking the thing up into pieces, 1, 2, 3, 4, 5, 6. You have 6 of these, and then that would be those are these 6. But these don't just take 4; they take 4, and then there's the actually what you're missing is, I think the thing that's missing, the reason why this doesn't look like 2 raised to the 2n is because, oh, I see. Yeah, this reduces easily. So, okay, I see the problem. Because this isn't including the sets themselves, right? Multiplying by the sizes of the sets themselves, which our algorithm is going to have to take into consideration. So if you do this, and you multiply each of these pieces by the sets themselves, which there's 1 of them. This has 2 of them. This has 4 of these sets. Right, there's another component here that's missing. This has 8, and this has 4. And if you do that, then you end up with 2 raised to the 4th times this whole thing. I was wondering, because the algorithm that I was thinking of was a lot simpler than I thought it would be. And then this reduces to 2 to the 4th times 2 to the 4th. All right, we already know this is effectively the sum of power sets. This is, yeah. Two raised to the 8th. Yeah, okay. That's why we got, yeah, because I was actually incorrect. I was missing a term here. The term that I was missing was counting the number of sets is fine, but actually considering the number of elements in each of these sets once you've actually counted the number. So there'd be 24 of these sets, but then there'd also be 4 per 24, which would give you, what do they call it? What is that? 16 times 6, which is 96. Or 4 by 24 is also, yes, 96. Yeah, yes. So anyway, let's go ahead and look into the next set of things here, which is, right, so let's get to our algorithm. Like, what was the idea that we had? Yeah, I was thinking about it, like there's something missing, something that was wrong. All right, so you have end symbols, and then we want to get, so, okay, how do we do this? I know I needed a pad left and pad right. I know I needed these routines. I think I don't need pad right, I think I just need pad left. So this is going to take, this will be a function. We'll give it a comment. Just S represents a sequence. Width is the final width of the sequence, and then C represents an element to pad the sequence width repeatedly. Actually, what's interesting is you could even call this like padding, pad sequence. Instead of an element, you give it a full-on sequence. And then you can say S with pad sequence. And then go ahead and say, and then what you're going to do is a pad left, you want concat count of S minus the width, excuse me, width minus the count of S, right? And you're going to take that many of those from pad sequence, and you're going to concatenate this sequence with S. Right, that pad's left. There's a pad right we can do as well, but we're not going to get into that. You can even do, yeah, I think this is fine. We'll do it this way. Right, and if your sequence is already greater than the width, then you final width of the sequence is the minimum. Call it minimum. Okay, pad left. And then we also wanted to generate binary. Call it generate binary strings, binary sequences. By the way, this throwing F in there is just kind of habit. It's not really necessary. I do that when I use like recursively memoized functions. That's I like to throw F in there. So what we want is N and bits, and we want to say yes, yeah. So just that's fine. These are numbers. What are we doing here? I want to take a range. We want to say get this range. Then range of n, going to map integer to string. Could could alternatively do this. Map this function to the range. And what we want is integer. Oh yeah, the way I did this is kind of funny or interesting. So yeah, we did 2 of these. So do integer to string of 2, and then pad left with the width is bits width, and pad sequence is repeat zeros. So you pad left. So toString pad left, and I think that's it. Oh, we did want to do something else too. We also wanted to map of, so we can do this. Okay, we can also, there's another mapping I want to do, which is int of x minus int of 0. Yeah, that's what we want. And that's going to convert this to integers. Yeah, okay. Oh, come on, man. Shoot. Problem is the map function. No. Come on, man. Alright. Mm-hmm. You can throw one of these in there. Interesting. Yeah, I guess that works. Oh yeah, it does work. Oh, that's funny, because this symbol, right, is going to push the result here. So that's interesting. I wonder if this works as nested threading macro here. I wonder. Let's try to test this out. Let's generate binary sequences. Oh. And we want n in the bits, so say 15 with 4 bits. And I anticipate we're going to have lots of testing here. So let's just go ahead and comment that out. Now, I don't think I'm going to finish this the next 20 minutes. So as you can tell, I'm kind of meandering my way through this. Let's try to generate these binary sequences though. Karnaugh maps. All right. Oh, yeah, I forgot about these. I need these. Uppercase, lowercase characters. There's the thing I was going to create here. Oh, did I already? I did. Interesting. Range. Drop. Take 26. I have these two characters. Oh. Okay. I mean, okay. Unmatched delimiter. Nice. Where? Excuse me. Where's that happening? Really, unmatched delimiter. Is it this one? I think it's this that's causing the issues. I was kind of hoping it wouldn't be. Like if we get rid of this, does this compile? I think it's gonna give us something kind of funky. No, that has nothing to do with this. I mean, I don't see an unmatched delimiter anywhere to be found. Where could that be? There's just an extra one of these somewhere. Wow. A little confused here. 4837. Why though? What do you mean? What do you mean? I don't agree. This is the one with 4837. This one? Oh, no kidding. I didn't even realize. It wasn't. Okay, got it. Okay. Oh, look at that. Oh, look at that. There you go. Wow. Amazing. Oh, where's 111 though? Oh no, it doesn't exist, right? It's 15. No, it should exist. What happened? Where is 15? 1, 2, 3, 4, 5, 6, 7. Oh, I know why. Yeah, I know why. Exclusive. Generate binary sequences from 0 to n exclusive as convert and return integers from 0 to n exclusive binary sequences in vector form. Okay. Okay, so fair enough. Generate these binary sequences, we pad to the left. Okay, great. So I want to use these building blocks. Now the thing we wanted to do ultimately though is, we got these upper letters and lower letters. We're going to create a symbol map as well, which looks like the following. We say kind of want something like this. We want to into a hash map, a concatenation of two different maps, and these are going to be a map, a list of range, so index to the letter, not the letter, excuse me, 0. And we're going to also create this set or list of, so we got these tuples, and we want to append to a list for each of these tuples. Also map these to the upper letters. So 0, so the upper letter is actually, it actually should be a 1, the upper letter. And the lower letter be 0. And these should be, yeah, it should be integers. We print the symbol map. That later. Yikes. Oh, excuse me. All right, these are zip maps. Duh. Yeah, there we go. I wanted to use that zip map. There we go. Neat. So now, we got our symbol map, we can pad left, we can generate binary sequences. Now I want to go to bed. I want to go lay down. Now I don't want to keep going. So the thing we have now, we want to consider, so I think I mentioned this before, right? We've got this, we can loop through, so we can generate binary sequences to give us a split, to use the zeros and ones as a split, and then we can rebuild the zeros and ones as something that's not split. So I'll show you what that would look like. We can say generated binary sequences. And we're going to use n in bits. N is going to be the number of symbols. Math power 2 n symbols. Convert that to an integer. Alright. And the number of bits, give me the number of symbols. So we're going to generate these binary sequences. Now what we want to do is, I guess, generate K-maps, we'll call it. I'll give this some commentary. Generate the given a binary sequence, a vector of binary numbers. Zeros and ones, assume that the ones represent unchanging elements of a K-map, and the zeros are the changing elements of a K-map, and generate corresponding sets that would represent a disjunctive adjacent group that, if present, K-map reduce would simplify the Boolean logic. Okay. Given a vector of zeros and ones, assume that the ones represent the unchanging elements of a K-map and the zeros are the quote-unquote changing elements of a K-map, and generate the corresponding sets that represent disjunctive at adjacent group. That, if present, a K-map would simplify the Boolean logic. I realize that's saying a whole lot while saying a whole lot of nothing at the same time. So we'll say, and we're also going to do something here, which is pre, and we'll say Boolean vector. So it's vector, Boolean vector, and then you could do further, ensure that it's a not just a Boolean vector, but also has zeros and ones in it. So to generate these K-maps, what we're going to do is collect collect the indices of the zeros and ones. So we're going to use a let in here. And we're going to say ones indices, which we're going to just range over. We're going to map, list, range, and the Boolean vector. We'll just say with indices. So I need to rewrite this multiple times. We're going to filter with this function AB, destructor. We're going to destructor and say B equals 1. There's another. No, it's fine. Destructor B equals 1 on with indices, and then map. To the first of these. Zeros indices. Almost the same thing, except now B has got to be 0. I don't know what I just did. Okay, looks like it's fine. Yeah. So I want to get the indices of these things because we're going to manipulate them. And what we're going to do to manipulate these indices is we're going to. This is interesting. I was thinking about this, how to do this. This is interesting. So first we want to build bit, what do they call this? Sequence, binary sequences. We want to generate these binary sequences. So we want to generate binary sequences of, we're going to say, the ones binary sequences. No, we don't even need to do that. We can actually do that like down here. Well, yeah. Okay. Ones binary sequences. It's going to be math power 2 count of ones indices. Convert this to an int. Can maybe do this. Ones. Even do this. Just call it just a get. Given a sequence of indices, turn a binary sequence for which we may later associate the given indices. Oh boy. So I forgot I can use this command instead of doing all that typing. I think we'll go to bed soon. I'll probably just stop midway through this and pick us up later. In say x equals count of indices, and then we're going to say generate binary sequences of 2 items, which are going to be x and x. Oh, okay, good. Math power 2 of x int of x. So we get the count. Generate binary sequences of that count. 2 raised to the value of that count. Integer. This should be fine. So 1's binary sequences. We'll say get binary sequences. So we can actually, we don't even need the 1's binary sequences anymore. Now what we want to do is use a list comprehension. And we're going to say x is get binary sequences of the 1's indices. And inside of here, we're going to have another list comprehension of get binary sequences of the 0's indices. And now this is very interesting, this part. What I was thinking was we're going to have a list, 2 things, and we're going to say take this list. We're going to return a list. It's going to have two elements. It's going to have the first element is x, right? But it's not just x, it's x converted to a symbol map. So we're going to look up in the symbol map. We're even going to use a let. I'm going to say let, or even, do we need a let? I don't really need a let necessarily. So let's take this list. We're going to have 2 things in the list. The first thing is going to be, it's not just x, it's going to be, excuse me. This is a binary sequence, x. You're going to map list of range over, not range, it's going to be map list 1's indices over x, right? So you're going to pair these off. And then you're going to map symbol map to each of these values, right? That'll be the first part of your list. And that we can make a set out of that. Yeah. Okay. That should be fine, I believe. And then we're gonna do something similar to create a set of sets over here. Now the way we do it is I probably can do something like this, like, well, it doesn't have to be. Yeah, I guess it's probably better to do it this way. Use a let. Sneeze. Excuse me. Oh, you know what it is? I use two different key combinations for the mic. I use Control-Alt-M and Control-Shift-Alt-M. Oh no, wait a minute. No, I actually just didn't hit the keys hard enough. No, we're fine. I just needed to hit the keys harder. Nice. We could probably also keep this kind of simple too. Just call this bin indices. I don't know. I don't know what to call this. B indices. Okay, sort of zip these up. There might be a better way to do this, but I've just been using the same routine each time. Just kind of zip my my values. So you can B indices now. So now we can map to our symbol map. Use it as a function to get the correct characters that we want. Also, this is wrong. So we don't want characters with this. Not this one. These are wrong. We don't want characters. We want symbols. Yeah. By the way. Okay. Alright, I'm gonna go to bed. Going to go to bed, but we can do one more piece here, which is binary sequences of the one indices. We can B indices, so binary indices. And the idea is that we get this set. Now, this portion is kind of interesting. What we're going to do here is we're going to concatenate a couple things. We're going to concatenate these bin indices. We're also going to create, I don't know, not this one. We're going to, I guess you could just do this again. Why not? Another sort of I don't know, call these Z. I don't know what to call them. And it's going to be zeros indices with not X but Y. Right? It's got the indices and the Y's. And now you can convert these to their appropriate symbols. You could even do better than that. You can concat these bin indices with Z and then map. Create this set. I think that works. So this is pretty interesting what you end up with here. It's pretty interesting. Call it K-Map matchers. So if K-Map matchers for 0110, right? Let's try that out. See how that goes. What does this do? Boolean vector 0, 1, 1, 0. Let's try that. What will that give me? Nope, there's a lot of changes we made here, so there's a small chance this won't even run. Oh wow, it worked. Look at that. Okay, well it didn't do what we expected, but it did run. Let's take a look at this here. Interesting. These were turned into integers. We can't just convert them to we convert them to characters and then strings and then symbols. Can we do this? Does this work? No, it's, yeah. Gotta convert them to characters and to strings. It's kind of funky. I'm not really sure how I feel about that. There you go. Neato. I don't really like that. Character, then string, then symbol. Seems kind of bad. But look at this. So you get C, and then you get this. Now, this, in my opinion, ought to be a set here. Yeah, it is. So these are sets of sets. So this list is fine, and this is going to be a list of lists. Actually, this is where the set's got to be, and outside here. What does that look like? Set of lists. I mean, really, it's a set of sets, right? Actually, it should be in 2 spots. I guess this was in the right spot then. This is a set, and this is a set, so I think they're both sets. I'm supposed to get a set paired up with a set of sets. And there you go. It does look. Now, what's also interesting is this ACBD doesn't quite. The sets themselves, they kind of end up in a funky spot, the symbols. But anyway, yeah, so CB, you would have to match this whole thing. If you would have, yeah, so CB is constant through all of these. That's basically what this means. And then you have 4 different things for A, little a, D, big A, little d, big D, little a, big D, big A, little d, right? 4 different possibilities. And then if you did something like this, it gets more involved. In fact, that's way more. 1, 2, 3, 4, 5, 6. Yeah, look at that. These are all the possibilities for 3 things being constant. There's going to be 8 of these, and then each inside of each of those another 8. Right, so each set has 8 things. Bunch of different possibilities. Gets cut off a little bit over here. So this is what we can use to generate the matchers that we want to use later. And what's going to happen is what we do is we just match all of these sort of second pieces, sort of just loop through everything that we've got and look for the subset starting with the largest values. What we're going to do is we're going to check that against if that's a subset, if any of these are a subset, starting from the largest ones, if any of these are a subset of the conjunctions, then you remove all of those from the conjunctions. You take the set difference and the result set. You're going to add the associated sort of smaller set. That's sort of the reduced form to the set of sets that you return. And that's it. You just process these matchers one by one in that way, starting from the largest sets and descending sorts of small sets, and you're done. It's a pretty interesting problem. Definitely took me a very long time, but overall was not too bad. And I mean, there's going to be, someone in the, what do they call that? Someone in the solutions here is going to have like a much more concise answer than what I have. But, I mean, what are you going to do? They're going to have a much more concise answer and probably more efficient as well, too. Not that I'll be sad. I'll be glad to see it. But, yeah, obviously, it's probably there are ways to make this simpler. I do think that this is a very interesting problem, and in particular, if it does take exponential time, 2 raised to the 2n time to by the way, I think 2 raised to the 2n is equivalent to 4 raised to the n. Right? Yeah, I think this is just 4 raised to the n as well. Yeah, taking exponential time is not great. But am I wrong about that? I don't think that's true. I don't think those are equal to each other. Taking exponential time is not great, but at least it can be done. And then, oh yeah, that's the reason why Karnaugh maps are useful in the first place. The reason why I even want to use these Karnaugh maps in the first place is that obviously this process that we just described, if it's exponential time algorithm, if it's an exponential time algorithm, then this saves us a lot of time. This Karnaugh map. Basically, the idea is that it makes use of the human brain's pattern recognition abilities, and so you can easily recognize patterns. And you don't need to use, you don't need to loop through all these exponential different exhaustive sort of search cases. You can just use your brain, and your noggin will be able to sort of figure these things out very quickly in each case, which is pretty interesting. It's very interesting that somehow your brain can come up with a faster heuristic than the brute force algorithm. I guess that's kind of what it comes down to, is your brain has some pretty fancy heuristics that it uses to figure things out very quickly, and pattern recognition ability. That's amazing. I mean, that's nothing short of amazing that you can use your brain's pattern recognition ability to solve an exponential time algorithm. It's pretty amazing. I wonder if you can solve. Now here's a real doozy. I wonder if you could solve, sort of showing p equals np. I wonder if you can solve exponential time algorithms by converting them to pattern recognition problems, right? Basically like Karnaugh maps, because you have such a thing as computer vision, right? So I wonder if you can use computer vision, program your computer vision machine learning program to solve Karnaugh maps, right? Using pattern recognition. And then what you do is you map exponential time algorithms to like something like Karnaugh maps, right? Reduce them to the pattern recognition of a Karnaugh map, and then use machine learning to solve the Karnaugh map really extremely efficiently. And then you have, if you're able to reduce that problem to an exponential time thing, then maybe you can solve extremely difficult problems in more or less intractable problems in reasonable time. I wonder if that's a thing. I wonder if that's a reality. That'd be pretty cool. That'd be a really interesting thing to work out. I think that would, if you could show that your machine learning program will always operate in polynomial time, I guess, then you could say that your algorithm is, then you have p equals np, right? Something like that. Although that's not really true, because I don't think the human pattern recognizing ability extends beyond, like, I don't think it extends to very large data sets anyway. And maybe it does. I don't know. I don't know if you can emulate like machine learning pattern recognition. It'd be more like, I think it'd be heuristic. It wouldn't be like provably linear time, but I mean it might be something that would be extremely effective in practice, which I think that something similar has been done for already for like real-time simulations, like when you have like game engines. I don't know though. I mean, basically I want to say that you can use machine learning to optimize a lot of stuff by creating like super fast heuristics, because there are game engines that do certain things, and you can kind of create machine learning sort of heuristic that runs extremely fast. There's a paper written about that. I don't know. Let me go. Thank you all for watching. I'll talk to you all soon. I'm not gonna finish this problem, but we're very close. There's like a couple more steps to add, and we'll come back to this later tomorrow. Talk to you all soon. Have a nice day. What am I missing here? Yeah, that's it. Just let me get going. All right. Take care.